Hello everyone, Saqib Khan here from the Spannovation Bridge and Seismic School. Today I want to talk to you about the two different pile depths of fixity. When we are thinking about the depth of fixity of piles, we should remember that there are two distinctly different meanings to this term. And a lot of the times we liaise with our geotechnical friends and we ask them for the pile depth of fixity. We have to absolutely make sure that we ask them for what we want and then incorporate it in our analysis appropriately. So over here I'm just showing you a very simple system. This is a single column bridge bent with the bridge deck sitting on top, and the column is supported on an oversized caisson or a driven pile. You may think of either one of those two scenarios, or this could be sitting on a pile cap with a group of piles underneath. Now if we are to do the seismic analysis of this thing appropriately, again we can use a single degree of freedom system here if the other piers are not extremely different in height and stiffness and all that. We will talk about some of those issues at other times, but really if I were to just take the system and I wanted to analyze it in a rather robust manner, I would come up with the PY springs. I would either ask the geotechnical engineer to provide me those or give me the soil parameters and let me know what PY spring formation I need to use to come up with the springs, and I can do that. Then I will shake the system, I get the period, I use the response spectrum and modal analyses to come up with the bending moments and shears and axial forces in the column and the caisson, and we design everything and off we go. However, that is a rather time-consuming process, and for a lot of projects we don't need to go to that sort of detail. So what we do instead is we come up with a depth of fixity and we use that concept in our design. So here I'm showing two more things. One is the bending moment distribution within the system, and the other one is just a single degree of freedom oscillator. I'll explain that in just a second. But this is just showing you the bending moment distribution in this system. If you were to run it using the PY curves, you'd get an answer that looks something like this. The maximum bending moment occurs in ground at a certain depth. So this DM max from the ground level to the point where I have the maximum bending moment could be thought of as the depth of fixity for maximum bending moment. And that's where if you knew your base shear appropriately and you knew where exactly this point occurred, you could just have a single degree of freedom system, fix it at the bottom, get your maximum bending moment, design your pile. However, it's not that simple to get that. What we're after when we are going to start our analysis in this simplified manner is to come up with a depth of fixity of the pile that gives me the same displacement between these two systems. So this system is going to displace through delta with all these soil springs and the entire length of the pile. This system has a much shorter pile length, which is certainly not going to be equal to this DM max. This D fix is not going to be the same as DM max. However, this value has to be such that when you shake this system, it comes up with the exact same delta as this system. That means that the stiffness now between the two has matched and our answers are going to be appropriate. Why do I say that? Let me just take a little bit of a detour into something a bit more theoretical, but I won't go too deep into it. I just want to make a point and then I'll bring it back to this situation. So without doing any derivation, I'll write the equation of motion for a single degree of freedom system, a mass damper system that is under the effect of earthquake loading. A lot of you will have already seen it. I will derive it at some point in one of our courses just to build from the bottom up, but let's just see that you have the inertial component, you have the damping component, and you have the stiffness component, and that's equal to MUG, which is the force due to the ground acceleration. Now I can divide both sides by M, and I am left with this. And I'll do a little bit more work here. I'll multiply and divide by 2 omega n. That's only on this term. And plus k over m u is equal to minus ug. This term 2m omega n is the critical damping ratio. So we get c over c critical times 2 omega n. And plus k over m is the square of the natural frequency of the system. This ratio of the damping to the critical damping is the damping ratio denoted by C. So we're left with 2c omega n plus omega n squared u equals minus ug. Okay, that's where I'm going to stop with the derivation, but all I want you to focus on in this equation is the fact that the only two things that the displacement or the acceleration of the system will depend on is the damping and the natural frequency. And when we're running the analysis, we're usually assuming the damping to be 2 to 5%, so that number is pretty much fixed. So really it all comes down to the natural frequency or the natural period of the structure. The natural frequency is given by square root k over m, or the natural period is given by 2 pi square root of m over k. Now you can see the most important thing here is this ratio of k over m, or m over k. So any two systems that have the same k over m or m over k are going to have the same natural frequency. And therefore the stiffness, given that the mass of the two systems is the same, is the most important characteristic, is the most important parameter to capture. And therefore this depth of fixity has to be appropriately calculated so that that displacement is the same. When the displacement is the same, we know that the two systems have the same natural period. When you have captured that natural period appropriately, now you can go into your response spectrum analysis, or you can just use the quasi-static analysis and apply the base shear, because the base shear between this and this are going to be the same. Once you have the base shear and the displacement matched, you can give those numbers to the geotechnical engineers. So typically what we do is we now only look at the caisson and we give that base shear F, the P value and the M value that we get at this location out of this exercise where we use this model, and then they go apply the springs and come up with the maximum bending location. Okay, so whenever you're starting, you should always think about the depth of fixity for appropriate stiffness, which will give us the appropriate period and it'll give us the appropriate base shear. At that point, you can turn that over to the geotechnical engineer, or you can come up with your own alpine model and come up with the maximum bending in your pile or your caisson. So just summing it up, at the very end, always ask for or try to determine the depth of fixity for appropriate stiffness so that you can get the appropriate period and the base shear. That gives you the appropriate forces at the interface of the column and the caisson. And once you've got that, now you can decouple this. You can just remove the caisson, you can have it separate and apply these springs and just apply the forces and get your maximum bending moment. It is much more simple to do it this way rather than have the PY springs in your global model, because those are nonlinear springs. And when we're running a modal analysis, that is a linear analysis tool, so we have to iterate many times on these spring stiffnesses to get to those secant stiffnesses that are compatible with the earthquake demands. Thank you.